Hello dear learners, in this class we will try to understand some emissions which originate from the sun and their causative mechanism, which is the solar flares. We will try to briefly understand how solar flare originates from the sun, and many emissions during that period of time, how they are relevant for the terrestrial earth or the earth's ionosphere. In the last lecture we have seen how solar activity is responsible for coronal mass ejections and solar flares, etc. Right. So, solar wind and magnetosphere. So we are trying to understand the sun and earth connection, sun and the earth. So we are referring to the geospace. Basically, we have seen the geospace is primarily filled with plasma, and we try to understand various properties of plasma and how it is different from a gas or from an ionized gas, what are plasma criteria, etc. So by geospace we are basically referring to the near earth space in which there is magnetosphere, ionosphere and thermosphere, because this region is the first point of contact when solar radiation or plasma or solar wind reaches the earth. We need to understand what can happen during this interaction, right? So the magnetosphere, like I said, is the topmost region of the earth's proximity or the space, geospace. The magnetosphere is the region of the terrestrial environment where the geomagnetic field has some dominating influence. So geomagnetic field, because of the earth being a magnet, has some dominating influence. So where we can say that the geomagnetic field or the pressure due to the geomagnetic field exceeds the solar wind pressure. This space is called as the magnetosphere. So we will try to understand in detail about the magnetosphere in next few lectures. But for the sake of definition, we can remember that the magnetosphere is the region of the terrestrial environment where geomagnetic field exerts the dominating influence. So the most important factor in this space is the geomagnetic field or the magnetic field due to the earth. Right. So as a consequence, how do you establish this dominating influence is that the energy density of the magnetic field exceeds that of the plasma. So here B square by 2 mu naught, generally referred to as the beta, or B square by 2 mu naught is the pressure exerted by the magnetic field, or the energy density corresponding to the magnetic field exceeds the pressure of the plasma. So plasma is now being treated, the solar wind plasma is treated as with a pressure P is equals to n kBt, where B is the magnetic field of the earth, mu naught is the permeability of the free space, kB is the Boltzmann's constant, n is the number of particles, number of solar wind electrons or protons or charged particles per unit volume, T is the temperature. So pressure associated with the magnetic field and the kinetic pressure are now being equated, and the regions where the magnetic field or the pressure exerted by the magnetic field is sufficiently large than the solar wind pressure, you call that region as the magnetosphere. A very simple definition, right? Now, what happens at the low altitudes, the magnetospheric low altitudes, the magnetosphere merges with the ionosphere. So, you have the ionosphere, or which extends, some of the ionosphere is also in the thermosphere, which is also part of the ionosphere, merges very well with the magnetosphere. So, in a continuum, these different regions of the Earth's atmosphere can be found, right? Now, in this lecture, what we will do is we will try to fundamentally understand the causative mechanism of a solar flare and some radio emissions which originate from the sun, because all these emissions or all the solar flares and the various electromagnetic waves or plasma outbursts during the solar flare have some impact or have some bearing on the terrestrial climate or the dynamical conditions in the geospace. Okay. So, the sun emits electromagnetic radiation over a wide range of spectrum or wide spectral range. It emits not only an electromagnetic radiation over a wide spectral range, it also emits a continuous stream of plasma which I am referring to as solar wind, and bursts of energetic particles, which are the coronal mass ejections, or the uh, events in which huge plasma is thrown into the solar system or the interplanetary space. So, sun is a source of all these three different types of energy outputs. Okay. The solar rotation varies with latitude from 25.4 days at the equator and 33 days at the latitude 75 degrees. So, this is what we have discussed as differential rotation. This topic or this idea is already given a lot of emphasis in the earlier lectures. So, what you can remember is 25.4 days or approximately 25 days near the equator. So, equator is rotating faster by approximately 7 to 8 days in comparison to polar latitudes of the sun. So, there is a continuous decrease of speed from the polar region towards the there is a continuous decrease of rotational speed from the equator towards the polar latitudes. So, the intensity of certain emissions received at the Earth therefore varies with the solar radiation. That is what a consequence of this is. Because of this solar rotation, the intensity of certain emissions which are originating from the sun varies as a function of the solar rotation. A typical average period for the for the case of Earth, watching or looking from the Earth, a typical cycle is 27 days. So, if you spot something from which you are recording observations or emissions, it may take approximately 27 days to come back to the same position on the sun. Okay. So, what is the point that I am trying to convey here is that solar radiation, solar energy is in these three different forms. Okay. And the variability in the amount of energy output in these three different forms may be roughly of the order of 27 days. Okay. And sun emits 4.6 10 to the power of 26 watts of electromagnetic radiation, or 4 10 to the power of 26 joules per second. The amount of energy that is being emitted from the sun is, you can remember the approximate order of this energy output, 10 to the power of 26 joules per second, out of which 1.4 kilowatts per meter square reaches the Earth, or 1.4 kilojoules of energy reaches the Earth per unit surface area per unit time. This energy number, or this number, is called as the solar constant. These things have been discussed, but they are now being referenced in a way so that it can help our further understanding, right? So, solar radiation over the activity period, over the 27-day period, remains more or less constant in the visible range, or even if you take longer durations of the cycle, you can expect that the solar radiation, the variability, I mean the amount of energy that you can expect in the visible spectrum will remain more or less constant. Only variation can be expected up to only 1% during local brightening called as solar flares. Solar flares are the only events during which you can expect some variability in the electromagnetic spectrum, that too in the visible range. Okay. So, we have already seen how much amount of energy is emitted in each of the spectral windows, all that. I hope you can recollect all those values or all those concepts to maintain continuity of what I am actually doing now, what I am actually telling you now. Okay. So, this increased intensity mainly lies in ultraviolet and X-rays and originate from the chromosphere and the corona. So, this variability is mainly lying in these spectral ranges. And where do they originate? They originate from chromosphere and corona. You remember these. Okay. The solar flare is what causes this variability. So, solar flare is a sudden brightening of a small area of the photosphere that may last between few minutes to several hours. Okay. So, solar flare, how do you define solar flare? We have already seen some characteristic features of the solar flare, but for the sake of definition, it is just a sudden brightening of a small area, a small patch on the photosphere. Okay. And how long this brightening can persist is it varies between minutes to several hours. Okay. And these flares are classified on a scale of 1 to 4 according to the area of the brightening when the sun is viewed in a particular wavelength, which is called as H alpha. Okay, at 656.2 nanometers. Okay. And even smaller brightenings, okay, are designated with S, which are called as the subflares. Okay, fine. So solar flares develop near the long-lasting dark areas called as sunspots. It is already very well established that sunspots are those regions around which the solar prominences will evolve or are seen. Okay, and sunspots by definition are dark areas with lower temperature compared to the photosphere and larger magnetic fields. Okay, so the regions of enhanced calcium and hydrogen alpha emissions is also known as the plages. So plages is one among the prominences seen on the sun. So solar flares are very important as they are sources of sporadic particle and electromagnetic emissions that affect the Earth's upper atmosphere. So this is what I wanted to actually emphasize, is that they are sources of sporadic particle emissions. So during solar flares, larger electromagnetic energy output can be expected at the Earth's upper atmosphere, which may impact photoionization, which may impact ionospheric electron densities, and so on. So many things. And at the same time, it can also bring in larger amounts of sporadic particle energy input into the Earth's atmosphere, which may also cause changes in the dynamics of the Earth's upper atmosphere, or more precisely, Earth's ionosphere. Okay, and how do you see them? Solar flares are seen optically with a typical temperature of 10 to the power 4 Kelvin. So they are relatively cool in comparison to the what you expect, right? They are relatively cool and can be significantly extended in the lower corona. So the regions, I have already talked about corona and the chromosphere, which are the prominent regions where solar flare activity can be found. Okay. So, the visible brightening that I am referring to as solar flare on the photosphere, the visible brightening is due to an enhanced plasma density, which is from 10 to the power 4, which can vary between 10 to the power 4 to 10 to the power 7 electrons per meter cube. Okay. So, these are the basic features or visual features, visual properties of solar flare. It is just a brightening whose temperature can be of this order, and which is relatively cooler temperature, and at the same time whose plasma characteristics can vary from 10 to the power 4 to 10 to the power 7 electrons per meter cube. Okay, the typical plasma concentration can be of this magnitude, and you characterize the solar flares in certain scale, and you also associated a S for referring to those small brightenings, which you call as the sub flares. Okay, and how much are we talking about here? So a typical flare releases 10 to the power of 25 joules of electromagnetic energy and emits nearly 3 10 to the power of 25 joules as particles. So the amount of electromagnetic energy released during solar flare activity can be of this order, 10 to the power of 25 joules. It's enormous. And at the same time, the amount of particle energy, the amount of energy emitted as plasma bursts is nearly thrice as much in comparison to the electromagnetic energy. So you remember these numbers. Okay. So this energy is stored. How is this energy coming out? This energy is stored in the magnetic fields, and it is released when the magnetic fields are annihilated. Okay. We will look at this mechanism, which is a very simple model to understand the flare evolution or the flare appearance. Okay. So just looking back at some very basic characteristics of solar flares, it is just brightening. And why we are discussing solar flares is there is a possibility that solar flares can induce variability in the sun's energy output. Okay. And where do you see this energy output to be changing? Originating from chromosphere and corona, and in the UV and X radiation. And it is characterized into 4 ranges on a scale, and brightening in small scales also refers to the subflares, which are denoted with a S. Okay. And the energy output during solar flares is enormous, 10 to the power of 25 joules. Now, this is the energy that is being thrown into the interplanetary space. How much of that energy makes it to the Earth's surface is a different story. Okay. But you remember those bursts that I have shown in the earlier classes, the amount of energy, the magnitude of energy that is there in those plasma bubbles is of this order of magnitude. Okay. And the solar energy, this energy is stored in the magnetic fields, and these magnetic fields, when they are broken or when they are annihilated, is subsequently transferred into the plasma, and plasma is moving out with this energy. The solar flare mechanism is shown in this figure. So, possible sources of various emissions which are of terrestrial interest are also shown here. Okay. So, the conversion of magnetic energy begins at the neutral point above the two sunspots. So, this is the neutral point which is shown right in the middle. These are the two sunspots with opposite polarity, south and north. So, between these two sunspots, there is a neutral point where the conversion of magnetic energy usually occurs. Okay. As the field collapses, the particles are energized and they travel away from the neutral points along the magnetic field lines. Okay. Now, this is where things start getting interested. Okay, so the particles are energized. So, the energy that is stored in the magnetic field is now being transferred to the particles, and conversion of magnetic energy to the plasma. Edit here. Conversion of magnetic energy to the plasma will accelerate the plasma and allow the plasma to move in different directions. So, as the magnetic field collapses, particles are energized and travel away from the neutral points along the field lines. And in this process, some protons may move outwards. These are the protons which are moving outwards. They travel towards the planets, outer solar system. Okay, some protons move outwards and eventually cause what are called as the solar proton events. Solar proton events on the Earth. So, these are the events in which large magnitudes of protons, energetic protons, are seen in the let's say in the 1 astronomical unit distance, or at 1 Lagrange point, or at geostationary satellite altitudes, etc. Okay, so the point is, much of the activity happens at the neutral point, and when the magnetic field collapses, the energy is transferred to the plasma. Plasma moves out, and in this process, some protons may move away along the magnetic flux lines, and these protons, when they reach the Earth, may be inducing what are called as the solar proton events on the Earth. There are more interesting aspects related to this. So, some of the inward traveling electrons are stopped in the denser chromosphere, and they produce Bremsstrahlung X-rays, which are significant in inducing ionospheric variability. So, these are the electrons which are traveling inwards, and they are stopped by the denser chromosphere. Okay, so it leads to the formation of X-rays, and if these radiation is traveling towards the Earth, they will induce significant ionospheric variability. And in the same region of the chromosphere, hydrogen is ionized by electron collisions, and on recombination emit the H alpha line. So, recombination, the hydrogen being excited by electron collisions, energetic electrons, in the same region of chromosphere, and when they recombine, they emit the characteristic wavelength or energy at H alpha. And this H alpha can also be seen from the Earth, and this is also referred to as the H alpha flare. So, in the region of solar flare, the corona is heated and emits soft X-rays and ultraviolet light with strong terrestrial consequences. So, different soft X-rays and ultraviolet which are emitted in the region of flare, where the magnetic field is collapsing, or where the hot plasma is being energized. So, this H alpha or X-rays and ultraviolet radiation can be seen from the Earth also. So, these are some of the electromagnetic radiations emitted from the sun during a solar flare, right? And all of them have strong bearing on the ionospheric dynamics. Okay. And apart from the X-rays, ultraviolet radiation, sun is also a source for several radio emissions. So, sun is source of several radio emissions, which allow us to study various aspects of solar activity. So, each and different bands of radio wavelengths reveal different information about the solar activity. Okay. Now, there is a constant thermal emission that is present all the time as a function of the temperature of the emitting region, right. So, you have 5800 Kelvin. So, there is a constant emission, that is thermal emission, because of that temperature, and different temperatures will lead towards the different wavelengths. So, solar origin radiation leaving the sun depends on the ambient electron density. So, which radiation actually reaches the earth or not depends on the ambient electron density. Why? This ambient electron density will decide a parameter which is called as the plasma frequency, and we know very well that the ionized medium with a characteristic plasma frequency is transparent to only those frequencies which are above it. So, an ionospheric medium or an ionized medium with a characteristic plasma frequency becomes transparent only for those wavelengths or for those frequencies inwards. Only the medium becomes transparent only for those frequencies which are above the plasma frequency. But in a neutral gas, it's not like that. But in a plasma frequency is a threshold frequency above which the wave propagation can occur. Okay. So, the famous or very well known wavelengths like the 10 centimeter wavelength originates in the upper chromosphere, and the meter waves from the corona corresponding to a temperatures of 75,000 Kelvin and 10 to the power of 6 Kelvin respectively. And thus, they are dependent on the emission intensity because of the temperature being these two values, right. So, in addition to these, the solar radio emissions, we have seen there are several radio emissions, right. So, there are 4 different types of sporadic emissions which occur from the sun, which are characterized between type 1 to type 4. Okay. So, solar radio emissions, depending on the intensity and the amount of duration, they can be characterized into 4 types, type 1 to type 4. So, type 1 refers to noise storms which last from hours to days. Okay. Type 1 can last from few hours to few days. What do they involve? They involve intense and sharp spikes of emission. Where? In the radio frequency. Okay. Where do they originate from? They originate from small areas near the sunspots, and they frequently start when the flare occurs. Okay. See, these solar radio emissions are coming from different parts of the sun, and the frequency of these emissions conveys a lot of information about where they are coming from, and at the same time what is going on from the place that they are coming from. Okay. All of this, if you are observing from a terrestrial planet, if you have to receive these signals, the receipt of these signals is critically dependent on the electron density, and the electron density governing the plasma frequency. Only those frequencies which are higher than the plasma frequency are able to be received, are able to travel away from the sun towards the terrestrial planets, where they are being received and further processed. Right. So, type 1 solar radio emissions, solar noise storms start when the flare occurs, and so from near the sunspots these emissions have been spotted. Okay. And they are probably generated by electron streamers in the magnetic field, in the magnetic fields above the sunspots. Okay. So, this is some basic information about the type 1 noise storms or radio emissions. Type 2 and type 3 are the most intense solar emissions or radio emissions, which are related to the solar flares, again to the solar flares. Okay. So, they consist of a number of sharp bursts at the start of the flares. So, it appears that many of these emissions can be observed when flare activity is going on, right. That means different aspects related to the solar flares can be understood by observing these emissions. Okay. Since we cannot carry out any direct measurements, we can only resort to the electromagnetic wavelengths which are coming from the sun, and understanding these radiations or understanding the fluctuations, understanding their intensity can lead us to understand about the processes on the sun itself. right? So, the type 2 and type 3 are the most intense solar emissions and related to the solar flares. They consist of number of sharp bursts at the start of the flares, and they also involve, or they also comprise impulsive bursts of microwave and hard X-rays up to 10 to 100 keV. They also involve microwave and hard X-ray bursts. Type 2 bursts last, they are very short lived in comparison to type 1 bursts, which are from few hours to few days. So, the type 2 bursts can last 5 to 30 minutes and are readily observed during solar flare. So all these aspects are they are different phases of the solar flare itself. So, the type 3 are more intense and are probably due to shock waves traveling from the flare. So, shock waves from the flare are seen as type 3 radio emissions from the sun. Okay. And hard X-rays or that type of activity, impulsive burst, are seen as type 2 bursts, and sharp and intense spikes of emissions are seen as type 1 radio emissions, right? So, the type 4 is a burst of long duration that follows some large flares and covers a wide band of frequencies. So, we have type 1, 2, 3 and 4. So, type 4 are bursts of long duration that are seen only during very strong solar flare activity. And the type 4 activity or the bursts are attributed to synchrotron emissions from high energy particles in solar magnetic fields. So, synchrotron emissions, when the particle is accelerated, the electromagnetic radiation that is emitted in the strong magnetic field can be attributed to type 4 emission. Okay. Now, we talk about solar activity cycles. In the earlier classes, we have briefly seen what are sunspots and what is sunspot cycle, the 11 years sunspot cycle. So, 11 years is the period of time when the poles get reversed from north to south, and in the next 11 years, the poles will take their original place if you assume t is equals to 0 to be the time before 11 years. Okay. And the point is, the sunspot cycle is of 11 years. Every 11 years, the leading sunspots will change their polarity. All that we have seen all that. Now, we will see a mechanism which has been developed to identify or to find out the sunspot number using different parameters. So, we know that sun undergoes periodic variations on several scales, several time scales. We have only seen two time scales. One very short scale is the 27 days. So, this is concerning any particular sunspot that you see, any particular emission or any active region on the sunspot, any active region on the sun. If you want to track the movement of this, it is approximately 27 days that you can see it occupying the same place watching from the earth. Okay. And then you have 11-year cycle, then you have 22-year cycle. So many other time scales are existing. So, the principal cycle of all this is the 11-year sunspot cycle. Okay. So, always remember this 11-year sunspot cycle is the most important, which can govern or which can directly affect all the ionospheric or the processes in the geospace. So, sunspots are generally seen between 5 degree to 30 degree, let us say north. Okay. So, the belt of latitudes that I am referring to is equator is 0. So, between 5 to 75 degrees. This is the region where you will find all the sunspot activity. Okay. The Wolf Sunspot number, capital R, is defined as k times f plus 10g. Okay. This is a number, a simple formula for getting the sunspot number. Okay. Where R is the number, f, small f actually is the total number of sunspots seen, each and every parameter. G is the number of distributed regions, either single spots or a group of sunspots. So, the G is the number of distributed regions. Okay. It can be either a single sunspot or a complete region which is filled with many sunspots, which is the sunspots have become a group. Okay. And K is the constant for the observatory related to the sensitivity of the observing equipment. So, K is associated with a particular observatory. The particular observatory becomes relevant because the equipment which is measuring this, observing these sunspots, has some sensitivity. Okay. And then this was started in 1848 by Wolf, and the R is still the principal index used in quantifying the solar activity. So, this is just a formula. We will try to understand more about this formula, the Wolf's number, the sunspot number, and how this can actually be helpful, or how even today this is relevant. That can be the most important question that we will try to answer in the next lecture. All right.